We have a circuit with a battery with some voltage E, and we have three capacitors. The capacitance is C1, C2, and C3. The goal of this problem is for us to first find the equivalent capacitance of the circuit. Then we're going to try to find the charge and potential difference across C1, and then C2, and then C3. In future problems, you're going to get circuits that are a lot more complicated, which involve both capacitors, resistors, and whatnot. But since we're just doing the capacitors right now, here's the following strategy that we're going to use for basically every capacitor circuit problem. So basically, the first thing we're going to need to do is find the equivalent capacitance for the circuit. The idea here is the following. Given the circuit above, likely there's some way that we can reduce it down to some circuit with just one capacitor. This is actually just given in part A, but a lot of the times we want to also find the charge of the potential. We're going to do the same thing. Next, what we're going to do is try to recognize when the charges are the same for a capacitor and when the voltages are the same. So maybe to do this, we should look at some of the physics behind what's going on to start. So I've sort of worked out the examples already, but now let's talk through it. So there's two scenarios for capacitors. One is capacitors in series, as depicted here, in which basically from the battery, if we sort of follow the line of what the current might do, it'll reach one capacitor and then reach the next one, and then eventually go back to the battery in sort of like one stroke. In this setup, the charges will be the same. We're going to have that the charge on the first capacitor will be the same as the charge on the second capacitor. You might remember from maybe lecture or maybe recitation that one way we argue this was to say that if one plate has a charge of plus Q, the opposite plate on the capacitor will have a charge minus Q, and those electrons need to come from somewhere. So they must come from the other capacitor in series. Maybe another way that you can try to justify this is the following. So we just saw me do this pencil thing in which I took a highlighter and just wrapped it around the circuit like this. And the way you can understand this is like, this is basically the current, I. And this current, which is the charge per time, only has one path around the circuit. And since the current must be the same and since charge is conserved, it must be the case that whatever it passes through is going to have the same amount of charge. So with that logic out of the way, we can basically show that the reciprocal of the equivalent capacitance should be equal to the sum of the two reciprocals. And doing that will yield the expression that CEQ is equal to, in the case of two capacitors, C1, C2 over C1 plus C2. Just for fun, if you wanted to, you could imagine that you had like n capacitors in series and try to figure out an equation for this more generally. And just for edification, how do we actually prove this? So first, and I guess you'll learn this later on when you do more resistor things, the voltage of the battery should be equal to the potential differences over the two capacitors, or however many capacitors that we have. Then we're going to use the relationship that charge is equal to capacitance times V, potential. And then if we make that substitution, on the left-hand side, we can write this as the equivalent capacitance circuit over here. So QEQ over CEQ. And that has to be equal to the potentials over the two capacitors. So in this case, Q1 over C1 and Q2 over C2. But we just said that the charge must be the same. And since the current that is drawn over here is the same as in the equivalent capacitor, these charges must also be the same. So by equating all the Q's together and then dividing it out, we arrive at the expression that 1 over CEQ is equal to the sum of the reciprocals. Now we can move on to capacitors in parallel. So in this case, the statement that's true is that the potentials across the two will be the same, and they actually end up being the same as the battery too. You have to remember that when we say voltage, this is basically the potential, and potential is defined at a point. So when we're in parallel, again, if we sort of take this tracing analogy, the start points and the end points of capacitor 1 is the same as the start points and the end points of capacitor 2. And because potential, sort of like gravity's potential energy, or gravitational potential energy, is defined by some sort of like difference and a reference point, these potentials should be the same. And using this expression, we can then show that the capacitance just add. So how do we do this? First, we're going to recognize that since charge can't be created nor destroyed, Q total, or equivalently, the charge that will be drawn by the circuit of equivalent capacitance, should be equal to the sum of the two charges, Q1 and Q2. We then again use the fact that Q is equal to CV to substitute C times V being the battery's potential, is equal to C1V1 plus C2V2. And then since we just argued that all potentials are the same, dividing out V gives us CEQ is equal to C1 plus C2. With all this ammunition now, we can solve the problem. So when you approach a circuit, I phrase this as zoom in and simplify. By this, what I mean is to look at the parts that you can simplify down to something simpler first, and sort of zoom out from there. I guess that was a little bit vague, so I'll try to show it. When I start the circuit, I see C1 being in parallel to C2 and C3. But C2 and C3 are in series. So the first thing I'll do is look over here and try to simplify this part of it. The reason I want to do this is if once I simplify this, my new circuit will become, I'm going to call this C1 and then C23. And then this new circuit that I'm going to get is going to be something that I can simplify quite easily. So with two capacitors in series, we know that 1 over C23, my equivalent capacitance, should be 1 over C2 plus 1 over C3. I know I've shown the expression before, but I'm just going to show a strategy here of how to get that expression. I'm going to multiply everything by all of my denominators. That'll give me, and I'll write everything out, the following expression. We're going to get a few cancellations. This denominator should be C2, sorry. Leaving out with the expression C23 or C2, C3 on the left-hand side. And on the right-hand side, I'm going to pull the C23 out to give me C3 plus C2. Then from there, I just divide by C2 plus C3, and I should get that C23 is equal to C2, C3 over C2 plus C3. So now I have the circuit over here where I have the same battery. I guess I'll write in E for the voltage, as we know. C1 and C23. And because these are in parallel, I can just say that CEQ is equal to C1 plus C23, or equivalently C1 plus C2, C3 over C2 plus C3. This is the most that I'm going to simplify it, and I think for an exam, this is about where you would need to end up. So if I wanted to write this as one circuit with one capacitor, it would look like that. So now we want to find the voltage and charge on each of the individual capacitors. So let's start with C1. So this can be really tedious, but my strategy for doing this is basically to start in the most simple circuit and then pull myself out. So in the most simple case, I have this CEQ. And this really isn't that helpful because I have no individual capacitor. So I'm going to pull myself out by one step. So here is my C23, and I'll put in orange my C1. This way I can sort of use my physics to figure out exactly what all the attributes are for this circuit. So remembering that the voltage is given by E, these two capacitors are in parallel. And we know from before, since they're in parallel, I know that V1 is equal to V23. That's what I'm going to call the voltage on capacitor 23. And this is also equal to E. But we also know Q equals CV in general, right? So therefore, Q1 should be equal to C1. So if I write my thing as a pair, so I'm going to write like C1, maybe in this order, V1, Q1 is equal to, in terms of things I know, C1, E, and C1E. So with that, we can now look at C2 and C3. So here again, I'm going to pull out by like one step. So let's remember where we were before. So this is the last circuit we had. If we pull back by one step, we get the circuit that looks like this. This is just literally the starting circuit that we had. So we have C1 on its own that we kind of don't care about anymore. And here we have C2 and we have C3. So what do we know? Since C2 and C3 are in series, we know that Q2, the charge on capacitor 2, is equal to the charge on capacitor 3, Q3. We also know the following. Remember that the voltage or the potential difference of the parallel branches are the same. So here we had some potential that's the same as the battery, E, and that's going to be the same over here. The only difference being in this case, we have that V23 was equal to E, as we did in the previous step, which is then equal to V2 plus V3. Because the total potential over a branch in series should equal the potential difference of the equivalent capacitor. So what can we do with this information? Well, we also know if we were to write this part of the circuit out as just C23, we know that Q23 has to be equal to Q2, has to be equal to Q3. This is because of charge conservation. We know that Q is equal to CV, so I'm going to write it this way. C23, V23 is equal to C2V2 is equal to C3V3. So maybe first, let's solve for the Qs, since we care about this for our problem as well. So Q23 is equal to C23V23 is equal to the equivalent capacitance being C2C3 over C2 plus C3. And if you remember, V23 is just the voltage of the battery. So this is our charge for capacitor 2 and capacitor 3. And then now I'm going to solve for V2 using this expression here. So I have C2V2 is equal to C23V23. Making my substitutions, C2V2 is equal to C2C3 over C2 plus C3 times E. And then if I divide by C2, this and this cancel, giving me V2 is equal to C3 over C2 plus C3 E. And similarly, what you should find is that V3 is equal to C2 over C2 plus C3 times E. So then if we write out our pairs as CI, QI, or sorry, CI, VI, and then QI, I think that was a convention I used before. get the following. For the first capacitor, we have C1, V1 is equal to E, and Q1 is equal to C1E. For the second capacitor, we have C1, V is C3 over C2 plus C3 times E. And then the charge was here, C2, C3 over C2 plus C3 times E. And finally, the last capacitor, sorry, this should be C2. The last capacitor, C3, then C2 over C2 plus C3 E. And then the same charge as the second capacitor. And that's how we solve the problem. So for this case, if it's just a capacitor circuit, the variant problems, there aren't really that many. I'm just going to say it like this. So I would say look through Halliday, with the textbook in general, and homework for extra problems. You can also sort of think of your own capacitor circuit that you can use and trade them among your classmates to see what you can solve for. Among these variants, there are also problems that sort of test these ideas. So if you remember, there was one problem that we saw in which we had a circuit. It was like a battery connected to one capacitor, C1. But the change that we made was that right here, this was a switch. And it could connect to another circuit over here with maybe two other capacitors. Another question I might ask is like, what is the final voltage? What is the final charge on all the capacitors and so on? You similarly had another problem that was just basically some sort of circuit jungle or of capacitors. So maybe it looked like this, or likely a lot more complicated. You can make it as complicated as you want, but you were given a plot of like the voltage of one of the capacitors as a function of the capacitance of another. And maybe you can use something like this to figure out a more involved problem. But aside from variance, basically the thing you need to take away from these kinds of problems is recognize when potentials are the same or when the charges are the same. And then similarly, recognize when they add. And a lot of these problems come down to your bookkeeping of algebra. So if you have a really complicated circuit and you're looking for the potential or the charge of one part of the circuit, what you're going to need to do is sort of backtrack from the most simple version and just keep track of your variables to remove what you, or to define what you need to know and basically remove out variables that you don't need. I highly recommend doing a lot of practice with these. I think that the concepts tend to be quite simple for a lot of students once you've done a little bit of practice. But the challenge comes in being clean with your algebra.